So, welcome to the new lecture again for this course, Fundamentals in Application Dielectric Ceramics. Let us just briefly recap the last lecture. So, in the last lecture we looked at we started doing thermodynamics of ferroelectric phase transition. And for that we took a free energy expression and we wrote it in terms of just the polarization. So, the term that was, so it was given as 1 over half A P square plus 1 over 4 B P4 plus 1 over 6 CP6 and so on and so forth minus of EP. And then we wanted to minimize this free energy as a function of with respect to polarization. So, for that we considered two conditions. We got two regimes. First is T greater than Tc when A is greater than 0, B is greater than 0, C is greater than 0. For that P is equal to 0 happens to be a root. So, as a result we get a minima in free energy like this at P is equal to 0. So, this is G, and then for T less than Tc the scenario changes. For T less than Tc the value of A becomes less than 0. So, the free energy shows this kind of behavior with roots at P plus or P minus. Okay. And in between there is a transition when A, so at T is equal to Tc, A becomes equal to 0. And this we termed as second order transition, in which the polarization gradually drops to temperature at Tc, and the susceptibility, if you write susceptibility 1 over chi, then it decreases to Tc before rising further below Tc. Okay. And in this state this is ferroelectric, below Tc, and above Tc it becomes paraelectric. Okay. And this analysis was valid for small values of polarization, and as a result and only in the vicinity of Tc we can do that. And this is also reflected. So, you can see that the value of 1 over chi is not discontinuous. So, 1 over chi is continuous at Tc. Polarization, which is called as order parameter, drops gradually at Tc to 0, and then it is the second derivative of free energy which is discontinuous, but not the first derivative, that is. So in this case, in this kind of transition there is no evolution of latent heat, and it is only the second derivative of free energy that is discontinuous. At second derivative of free energy is nothing but your specific heat. Now, let us look at the little bit detailed analysis of second order phase transition as to how do we progress it. So, for the second order transition we wrote the energy or maybe we will do the analytical treatment later if we get time, because let us first do what we call as let us look at the first order phase transition scenario. So, first in the previous part we considered that for second order, for the condition when A is greater than 0, B greater than 0, C greater than 0 at T greater than Tc, and A less than 0, B greater than 0, C greater than 0 at T is equal to T less than Tc, we termed it as a signature of second order phase transition, right. Now, let us say what happens if we consider a different scenario. So, another scenario is A less than 0, B less than 0, but C is greater than 0. Now, in this case what happens is that when you plot the free energy versus polarization, so let us say this is G, this is P. In this case what happens is at temperature T, at temperature let us say very low temperatures, let us say at a temperature something which is so this is let us say a temperature T less than a temperature called as T naught, okay, which is less than Tc. Okay. So, this is where we have a free energy minimum. So, let me just if I draw the line a little bit here, that is more appropriate, and this is polarization. So, this is the case at very very high temperature, when we are at a temperature T greater than Tc, then our situation is something like this. The free energy change sort of, so this is at T greater than Tc, and at this value, so here we are saying that B is less than 0, C is greater than 0, and we are looking at the change in the sign of A. Okay. So, for this A is greater than 0, and at this point what happens is that A is less than equal to 0, which means in between some change happens. The change that happens is in such a fashion, so that we have this we have a change like this. So, this is at T is equal to Tc, at T is equal to Tc we have A is equal to 0, at T greater than Tc we have A greater than 0, and let us say at a temperature so this is at a temperature T is equal to T naught, which is lower than Tc. At this temperature A is negative. So, what we see is that with the, so C is basically the quadratic coefficient, B is the quadratic coefficient. So, with the quadratic coefficient being negative, even if T is greater than T naught, so T naught is the lower temperature than Tc. So, in the previous case we saw that we have termed this temperature as Tc, right. Now, consider this Tc as T naught for at present. So, even if T is greater than that particular T naught, with this B being negative, the free energy plot has some subsidiary minimas as against as against in the previous case. So, what happened in this case is at T is equal to less than T0, we have this minima, which is fine, which is the ferroelectric state. At T is equal to T naught, we again have a similar state, but at T is equal to Tc, which is higher than T naught. At higher than T naught, in the previous case it would have been just one minima, but what we have in this case is the transition temperature is sort of little weird here. So, in the previous case T naught would have been the transition temperature, because you have a situation like this and then you have a single well, but in between what we observe at a temperature called as Tc, that we have this sort of a subsidiary minima at P is equal to 0 also. Instead of having a maxima, we have a minima. This kind of transition basically is called as a first order transition, where we have a sort of, you can say, a transition state at T is equal to Tc, where we find 3 minimas, and these 3 minimas gradually shift to 2 minimas as the transition temperature is lowered a little bit. So, T is equal to Tc is somewhat you can say funny state, something weird happens there. So, what happens is that as you reduce, so as a function of temperature, we can see that sign of A changes, right. So, at T greater than Tc, A is positive, and at T less than Tc, let us say all equal to T naught, A becomes negative, and at T is equal to Tc, the A is equal to 0. It is similar fashion, but the polarization, but the change in free energy curve is rather different. Instead of, so in the previous case what we obtained was a behavior like this. You have behavior like this and then you have a behavior like this. Here the free energy shape is sort of different. It does not show a perfect minima, it has a sort of a change in slope at this point and then a minima. And then at T is equal to Tc, instead of having just one minimum, you have 3 minimum with one subsidiary minimum. So this, so basically as a function of temperature, as you change the sign of A, this, so basically we have a thermodynamic situation of 3 minimas at T is equal to Tc, and this Tc is higher than the T naught at which you would have otherwise seen a double well. So just below the temperature at which you see the double well, you sort of see a triple well, and this triple well is basically, so you can say that between Tc and T naught there is something funny happens, and basically you can say the unpolarized state, so basically what happens is that you can see that these two minimas belong to polarized state. This minima belongs to unpolarized state, which means between Tc and T naught we have a coexistence of unpolarized state and polarized state. So this is what happens in this range, the coexistence of unpolarized phase and polarized phase. And this is more like liquid solid transition. When you transform liquid into a solid, right, all of the liquid does not convert into solid altogether, or all of the solid does not convert into liquid altogether. There is a range of temperature when liquid and solid coexist. You can explain this in case of solidification on the basis of undercooling and energy required to create any critical size and so on and so forth. Perhaps similar explanations can be given here, that to nucleate a stable polar phase you need to wait for some time, some undercooling is required, probably similar sort of arguments can be made. But nevertheless what happens, this funny state of free energy well that you see, a triple well between temperatures Tc and T naught, is basically suggests that you have coexistence of two phases, and this kind of phase transition is called as first order. And when you make measurement of such a material, the polarization sort of goes and then drops boom at Tc. And if you measure susceptibility 1 over chi, then this is Tc. The susceptibility shows a funny kind of behavior. Susceptibility shows a discontinuity at this temperature, and if you extend this below, this is the temperature T naught. The extrapolation of susceptibility on the right hand side makes an intercept on the temperature axis at a temperature T naught, and between these two temperatures we have coexistence of polar and non-polar phases, very similar to what we can say solidification, in which liquid and solid coexist despite being a pure metal. Pure metal does not have a pure metal does last as a liquid solid region because of need to nucleate stable nuclei. Similarly, probably here you have a region between T naught and Tc when the material has these 3 minimas. What it means is that out of these 3 minimas, 2 belong to the ferroelectric state and 1 belongs to the unpolarized state, and these two states, polarized and unpolarized states, coexist between T naught and Tc. So this kind of first order phase transition is very similar to, you can say, liquid to solid transition, where we see a sudden drop of polarization below at Tc. Okay, so you can see this is ferroelectric, this is paraelectric, and you have sudden drop. So, polarization is decreasing, but it is not decreasing as gradually. It decreases and then boom goes to 0 and sudden drop, and then you have a discontinuity in one over chi at Tc. So, this is the fundamental difference in the first order transition. In the second order transition, if you now plot in the second order transition at Tc, the susceptibility goes as like this. This is 1 over chi for second order, but for first order what we have is something like this. This is first order. So, in some sense a second order transition is more gentle, it happens gradually, whereas the first order transition is abrupt, sudden. So, this is very similar to what we call as liquid to solid, because the whole structure has to be rearranged, the complete breaking of bonds and then complete. So, there is a sudden change in for example, enthalpy, you have latent heat of evolution. So, first order transition is depicted by latent heat, whereas in second order there is a gradual change, as a result there is no latent heat. So, here in first order what you see is the first derivative of free energy is discontinuous, whereas in case of second order we see that the second order. So, here del G by del T is discontinuous, right, and in this case del 2 G by is, this is the classic difference between the first order and second order. So, and in case of polarization, so polarization in the second order will go in this fashion, this is second order, and in case of first order it will go boom, this is P first order, and polarization is nothing but the order parameter, right, which can be related to free energy. So, basically as we say that the first derivative is discontinuous. So, you can see that here the first derivative is discontinuous, and in this case the second derivative will be discontinuous. So, that is the fundamental difference between the two phase transitions, the first order and second order, and there are quite a few ferroelectrics which show this first order phase transition. So, materials second order, as I say, is as I said earlier, is shown by materials such as Rochelle salt, etc., whereas and also for example lithium niobate, it shows a second order phase transition, whereas first order transition is shown by materials such as barium titanate and many other perovskites show a first order phase transition. So, this is what it is, and this is also manifested in the other thermodynamic parameters. So, we have not gone into entropy and specific heat and so on and so forth, but for the sake of understanding you may think that for the first order phase transition the polarization is discontinuous, it drops suddenly at T is equal to Tc. Susceptibility shows a discontinuity at T is equal to Tc. For the second order, polarization drops gradually to 0 at Tc, whereas susceptibility is continuous. It goes to 1 over chi goes to 0 and then again increases below Tc. So, this is what the main difference between the two polarization mechanisms. So, now what we do is that we will do a little bit of let us see if we have time to do any detailed analysis, but let us first do some analysis of second order transition first. So, in case of second order transition, if you look at the free energy specificity, so we can say for the second order transition polarization is a continuous function of temperature. Okay. As a result, there is no latent heat evolution, but there is a discontinuity in second derivative, which is nothing but specific heat. Okay. This is for the second order, and in the second order case, let us see if I can give you the expressions for susceptibility. So, for susceptibility at T greater than Tc, I can write the susceptibility as C divided by T minus Tc, and this is equal to 1 over A that we saw earlier, and this can be proven easily because we can write this del G of del P as equal to E, which is equal to AP, okay, ignoring the higher order terms. So, basically chi A will be equal to A inverse, right, and we know that chi is equal to C divided by T minus theta from the earlier analysis Curie-Weiss law. So, now you can just make the correlation. You can say that this A is equal to T minus Tc divided by C, which is equal to 1 over chi A, where theta is equal to Tc, okay, just the correlation of this. Now, at T less than Tc, let us define the susceptibility chi as chi B, okay. So, chi as chi B is calculated that we first calculate del G by del P, which is equal to E, this is AP plus BP cube. So, 1 over chi B is equal to del E by del P, which is equal to A plus 3 BP square, right. Now, so basically this susceptibility is chi B at this temperature. So, neglect the terms, we have neglected higher order terms, that is P to the power 6 and above. You can see here we have only taken the P square and the P to the power 4 term, all right. So, for small fields, if we say that P is equal to Ps, then in this region we can write this Ps square can be equal to minus of A divided by B, and this comes from basically the previous analysis of, if you do del G by del P at T is equal to 0, if you do the minimization, then we will get AP plus BP cube, that is equal to 0, okay. So, if this is, and if you do the minimization, then we can, so there is 1 at P is equal to 0 the root, but the other thing will be Ps will be equal to Ps square will be equal to minus of A divided by B, right, from the free energy minimization. So, at constant temperature, if you take the derivative of free energy with respect to polarization for a stable equilibrium, then we have these polarization values. So, if these are the values, these are the non-zero values of polarization. So, of course, at temperature lower than Tc, P is equal to 0 is not a root, this goes for maxima, right. So, what we have is the non-zero root at T less than Tc, which is P. So, Ps square is equal to minus of A divided by B. So, 1 over chi B can be taken as A plus 3B into minus of A divided by B, and this is equal to minus of 2A. So, 1 over chi B can be written as 2 into Tc minus T divided by C. So, you can see that in the first case 1 over chi is T minus Tc divided by C. In the second case, it is 2 into Tc minus T divided by C. That is why when you look at the susceptibility at Tc, the slopes are different. So, you can see that 1 over chi has twice the slope that so it will be something like this. This will have slope of 1 and this will have slope of 2. 1 over chi versus temperature, this is at Tc. These are very approximate analysis, they are not very accurate analysis, but if you do accurate analysis they will become very complex. So, but the simple analysis with simple assumptions helps you to understand how the susceptibility varies as a function of temperature and what is its behavior near Tc. Okay. So, this is what is about second order transition. We can do a simple analysis of the susceptibility for phase first order transition as well, which we will do in the next lecture. So, what basically we have seen is the difference between the first and second order transition, the first order transition, qualitative analysis of first order phase transition as to how the free energy versus composition diagram, free energy versus polarization varies across temperature, and we see that the subsidiary minima at P is equal to 0 between Tc and T0, and this is basically reminiscent of coexistence of polarized phase with the unpolarized phase, because the two minimas belong to polarized phase which are non-zero. The minima that is at P is equal to 0, it belongs to a unpolarized phase, and they do coexist together. So, we will stop here, we will continue this in the next class with further discussion on ferroelectrics, and then we will look at the application of three kinds of materials that we have discussed. Thank you.